So today I will explain my joint work with Kengo, Hirata, and Wakizaka on concurrent quantum separation logic for fine-grained parallelism. So in this work, we propose concurrent quantum separation logic for modularly verifying quantum programs with fine-grained parallelism. Compared to existing quantum separation logics, our logic is the first to support concurrency and the sharing of quantum resources, and can verify various non-trivial quantum programs. And compared to, and below we illustrate an example of such a quantum programs. First, I start with a brief introduction to quantum computing. Well, quantum things may look fancy, but please take it easy. You need not understand them 100%. Honestly, even I don't. So the basic building block of quantum computing is a qubit or quantum bit. While a classical bit can only be either 0 or 1, a qubit can be an arbitrary superposition of them, which is technically a linear combination. For multiple qubits, we technically consider the tensor product, which accommodates exponentially many superposition of exponentially many classical qubits, classical bits. And please keep in mind the notation used for tensor product or composite state. And the gate applied to qubits are restricted to unitary matrices or especially linear maps. And for example, the atomic gate gives a superposition by turning 0 to 0 plus 1 and 1 to 0 minus 1 with some coefficient. And also CX pronounced controlled X gate operates on multiple qubits. So it's a bit tricky. The result of any quantum computing can be obtained by measurement, which lets the quantum superposition converge to a classical state with a probability determined by the coefficients. Here is an example of a quantum program or a circuit. It applies the atomic gate to X, followed by the X gate on Y controlled by X, and finally measures both qubits. Starting with 0, 0, after applying the two gates, we get a superposition of 0, 0 and 1, 1. And after measuring it, we probabilistically get either 0, 0 or 1, 1, which is stochastically dependent between X and Y. So this is a typical example of an interesting phenomenon called quantum entanglement. Mathematically, an entangled state cannot be simply expressed by the tensor product. Now we are ready to discuss the motivation of our work. Our work addresses parallelization of quantum programs. As is the case with quantum classical computing, it is a promising way to reduce execution costs. We illustrate in an example of parallelizing two circuits with the latter made atomic. And a clever scheduler can produce the efficient circuits shown on the right-hand side. But the scheduler is also free to execute the two sequentially in either order. As observed here, parallelization allows exponentially many execution traces. So we need a modular program logic for verifying parallelized quantum programs, which is non-trivial. Typically, the correctness of a parallel program is the uniqueness of the output. To achieve this goal, we propose concurrent quantum separation logic, which has the following notable features. First, our logic supports parallel execution of quantum processes. And second, it supports shared quantum variables, even when there are apparent right races. And third, our logic supports atomic expressions for non-interfered embedding of quantum circuits and parallelization. So from now on, I will explain our work in more detail. Our target language looks like this. It has primitives for quantum operations, and parallel execution and atomic block for concurrency, and classical heap operations and control flows. And here is an overview of our logic. First, as concurrent separation logic, the Hoare triple is equipped with an invariant, which is what is accessible at each atomic step. And the syntax of the assertions is shown on the right-hand side. And we have all the standard separation logic connectives, and also standard proof rules on them. And like the classical heap points to token, we introduce the quantum points to token, and which owns and asserts the state vector psi of qubit x. We can freely apply a quantum gate if we update the vector of the quantum points to token. Separation of points to token means not only disjoint ownership, but also disentangled qubit states. Also, we newly introduced a proposition called the qubit token. It asserts that the qubit x is alive or allocated, but its state vector is unknown. We have more interesting proof rules, which I will explain soon. In this talk, I will explain and demonstrate our logic with this simple running example. It applies non-commuting gates x and Adamar to y in parallel, which is apparently a right race. But still, technically, this is no real race condition. 0 controlled x and 1 controlled Adamar do commute thanks to the controls by the case where x is 0 or 1, respectively. Our goal for this example is to prove this Hoare assertion, which gives the output of state vector precisely. The challenge in this example is that both processes can write to y simultaneously, because x can actually be a superposition of 0 and 1 in the quantum setting. So we need to distribute the write permission on y to both processes. How can we do that in a sound way? Our idea is to support a quantum version of a case analysis over the basis of a qubit. In this example, we split into two worlds where the vector of x is 0 or 1, respectively. In each simplified world, only one process writes to y. For example, if x is 0, then the one-controlled Adamar gate does not change the state of y. This successfully eliminates the apparent right race and enables the standard separation logic reasoning. This idea can be formalized as the following rule for taking the This idea can be formalized as the following rule for taking the linear combination of Hoare triples. It decomposes the target state vector in some basis psi and psi prime in the precondition, and then combine the outputs respecting the coefficients alpha and beta. Technically, we have the side condition that Q and I are precise or represent a unique or no resource. Now, using this rule, our goal boils down to the two sub-goals shown below. Now we can prove the sub-goals by resource sharing via invariance, a standard technique in concurrent separation logic. So here we show how the first sub-goal is proved, and the second one is proved in the same way. So we want to reduce this sub-goal to the two Hoare assertions shown at the bottom. For that, we can simply move the points to token of x into the invariant, which can be accessed by all processes at all processes at every atomic step. The proof rules for invariance are shown below. Now our proof is almost done. The whole assertion on the left-hand side can be proved easily. But how can we prove the whole assertion on the right-hand side? To prove such situations, we introduce the following novel proof rule for the qubit token. By this rule, we can get access to the points-to token for the qubit each atomic step. We call this the anti-frame rule by atomicity for the qubit token because it technically adds a frame to the hypothesis instead of removing it as in the well-known frame rule. This rule allows atomic writes to the qubit that is temporary or restores the qubit state after the execution is finished, which does not interfere with other processes which can freely access the qubit. In our example, the one-controlled X gate does not update Y when X is 0, so we can use this rule to complete the whole proof. As a summary, we illustrate the complete proof of the whole assertion for this simple example. Of course, our logic can support much more complex examples, including one we showed when motivating parallelized quantum programs, and essentially we can use the same technique for the simple example. And interestingly, we can even verify parallelization of arbitrary commuting matrices. This is because mathematically, any commutative matrices are always simultaneously diagonalizable. We can use the linear combination rule for verifying this. So I was a bit in haste, but we finished this part. So finally, I will discuss our ongoing extension to probabilistic reasoning, which is interesting on its own. We want to support quantum measurements. And the primary challenge for that is to precisely reason about probabilistic behavior. And in quantum computing, the standard precise model for that is a density matrix, which is roughly a probabilistic distribution of state vectors modulo some equalities. Our idea is to refine the approach of demonic outcome logic, the work published in this proposal and lead authors by Noam Zilberstein, organizer of this TPSA. We are also based on a concurrent separation logic variant of that work. A key mechanism is a probabilistic combination of logic assertions. This solves the limitation of the existing quantum separation logic in particular. And for the model, we introduce a new mathematical structure called convex PCM, which is a hybrid of convex space and partial commutative monoid. And here is the teaser of our probabilistic quantum separation logic. So unlike demonic outcome logic, we introduce the concept of convex assertions with the convex Hoare modality related to the idempotence of the probabilistic combination. Also, we manage return values as resources in separation logic, which is useful to model probabilistically varying return values. And for quantum things, we make the points-to token assert a density matrix instead of a vector, following the probabilistic combination. And we can naturally support measurement. So finally, this is the conclusion of our talk. For future directions, we are interested in more powerful concurrency reasoning and also automated. Oh, what? Okay, so for future directions, we are interested in more powerful concurrency reasoning and automated optimization of quantum programs. So that's all. Thank you for listening. Thank you.
My intuition, which is vague, is that you proceed by kind of case analysis. But when you have loops, it goes unbounded number of cases. So can you show your loop rule, the rule for the loops?
So I haven't shown the. Okay.
Yeah,
So
you
thank.
can do it.
Okay. So thank you for the question. So so basically, the case analysis rule is kind of the same thing as the disjunction rule in the usual Hoare triple. This like case analysis over the disjunction on the precondition, kind of. So like, and for while loop, so we can just use the usual reasoning rule. So if we target partial correctness, we can use invariant-based reasoning as usual. And if we target total correctness, we should use some other principle. But basically, it's just the same with classical computing.
And it is complete.
Actually, so I think we haven't precisely shown that, but so for non-concurrent fragment, I think the logic is complete.
Yeah, so the main crux of quantum is, of course, entanglement. So when entanglement is in play, do you have any inconsistencies with any of the Hoare triple proofs?
So basically the answer is no. So we support any entanglement. So this is because our quantum points to token is multi-qubit. So yeah, this will explain. So the qubits for the quantum points token can be multi-qubit, and like after applying some gate like CX gate, we do have entangled state on this part. So we can like just support quantum entanglement. But so quantum entanglement is actually a very good question, especially for the anti-frame room by atomicity. So technically, we actually implicitly linearly decompose the background state so that X is not entangled with any other state. So I think this can be an interesting thing about entanglement.
Thank you. Let's thank Yusuke again.
Thank you.